Hello everybody, I hope you're all doing well. I'm just making a very quick little video that's going to go over again some of the essential elements of doing principal component analysis and how we go about making decisions related to the retaining of principal components, how we interpret those principal components, as well as what we can sort of do with the scores afterwards. So all stuff that is kind of similar to what you'll be doing in your mini assignments. I'm going to talk about this paper that came out just recently that I think is pretty cool. It's about Gen 2 penguins, and it's a study in which they went and collected different samples at different locations of this species, and then they collected a bunch of morphometric data about it, and then they did some morphometric data about bill height, culmen length, radius length, manus length, lots of different sort of things, and then they performed a principal component analysis on it, and used that to try and make a case that there was sort of multiple different species. It's not just one species. Now, what we're going to talk about is the principal component aspect to it. And what's really cool is you can actually go to this paper, and under the supporting information, you could actually download the file. And I've already gone ahead and done so. It'll be associated with this video called Gen 2, and then we can load that data into into our R, and we can see that here is the data itself. It has where the collection came from, whether it was a male or female unknown penguin. The things that are relevant is lineage here, and then for later on. But for now, the thing we're going to focus on is the things in rows 5, 6, 7, 8, 9, 10, 11, 12, and 13. All of these different variables may be correlated to some extent with each other, so there may be a fair amount of redundancy. So if we were trying to describe, the shape and size of penguins, rather than do a half dozen or more different ANOVA tests or Prescott-Wallace tests to look for differences between lineages, what we like to do is try to be efficient and try and find a way how to describe these more effectively. So that's where principal component analysis comes in. So we can make a penguin PCA, and we're going to use our printcomp function. We're going to look at the Gen 2 data set, and we're going to only want to look at the rows that have numeric measurement data in. So that's going to be all the rows, but only the columns that are columns 5 through 13, which corresponds to everything from culmen length all the way through to MTL average. Now, the thing we have to decide is whether we want to use correlation equals true or correlation equals false. And to illustrate these things, I'm going to make two different models that sort of show you what happens. What you're essentially saying here is you're saying correlation is true, is that each one of these variables is going to be scaled to be equal in their variance and their standard deviations prior to constructing those new ordination systems, or if you use cor equals false, that you're not going to do so, and the things that vary more are going to have a higher weighting when drawing that line. Now, whichever one you choose, true or false, it's up to you. It's a subjective decision. What we can look at is the summary of these. So we look at the summary of both of them. Both fit on the screen. So what we do is we put in 9 different variables. We get 9 variables out. But the decision about whether to use true or false does impact the amount of variances explained by each one of these different variables. So if we do the standardization first, we see that component 1 explains 64% of the variation, and component 2 explains an additional 11% for a cumulative 75%. And if we were going by the 80% rule, that we would probably want to retain at least 3 principal components to bring us over 80%. Now, if you had used principal component false, in this case, component 1 explains far more variance than 74% compared to 64%, and to get over 80%, you might have only to take 1 and 2. Now, if we're using the Kaiser rule, we're only looking at eigenvalues that are bigger than 1. In that case, you would say, 1 and 2 is sufficient because they both have standard deviations greater than 1. Everything below it. If you're looking at this other one, that takes us all the way down to component 7. So these different rules are useful, but they don't always give you the same results. We can also look graphically at those eigenvalues and look for drop-offs. So if we look at the first one, we see a pretty big drop-off between the first and the second, so maybe only principal component 1 is what you want to care about. If we look at false, also the same kind of patterns. So there are just subjective decisions that we get to make that determine how many components that we're going to retain. And the reason why we don't retain all of them is because some are more informative than others, and we really don't really necessarily care about every single one of them. We want to have the ones that have the most bang for their buck. Now, once we've decided what component we want to look at, it's worth looking at the loadings of them. So again, we could look at the loadings of both of these. And I've showed you in other commands how we can sort of show all the different values, but for now we're just going to skim along here. And you can see that if we're loading is true, that all these values are roughly of the same magnitude, and they're all positive. So in that case, that the bigger you are, the bigger the beak, the bigger your flipper, the bigger your radius, the deeper your beak, generally you're going to have a bigger component 1 score. And smaller birds with smaller beak, shorter beaks, smaller radiuses, smaller flipper are going to have more negative component 1 scores. If I showed you the loadings for the false, we're going to see something slightly different because there's a different set of assumptions in there. In this case, that the biggest loadings are here of the malus length and the MTL length. So those are things which bigger individuals have more positive scores, and all these other ones are much smaller. So we kind of only pay attention to the things that have really big loadings in them. If we look here in component 2, component 2, we have a big negative is the biggest thing here. And this is interesting because when R does these calculations, what is a positive versus a negative really means nothing to R. It essentially just fits these axes, and the idea about what is a positive and negative is entirely arbitrary and random, as we'll sort of see in a second. But here, essentially, individuals with big MTLs will have large negative scores, and individuals that have small MTLs will have big positive component 1 scores. Now, we can also visualize these with biplots. So I could look at and this plots component 1 and component 2 with all the individual data points on it, and the different variables are illustrated by these sort of vectors. And the bigger the arrow in the direction in the dimension we're interested in, the more meaningful, the bigger the significance. So in this particular case, we can see here that MTL was big and negative in component 2, and that's why it's sort of going down. And that all these things were roughly of the same magnitude in the positive sense when we were talking about component 1. Now, I'm going to show you the biplot for the true one. And you can see that that here in that first component, they were all roughly the same in the same sort of direction. Now, I'm going to compare that to the figure in here, which is a little bit easier for us to do. They've obviously done a little bit of more work to make this look nice. And the thing you should notice here is that their biplot is the mirror image of our biplot. So when they ran R by chance, their R made their loadings all negative, while ours are all positive. So ours is the mirror image, and if we were looking at their loadings, all their loadings here would be negative instead of positive. So let's look at that plot. So just because it's a little easier to take a look at, and when we're looking and trying to interpret them, think about the dimension, the distance in the axis we're interested in. So principal component 1, in this particular case, has a lot of negative loadings for all these things. So bill height, bill width at the base, bill width at the goddess angle, common length, manus length, middle toe length, radius length, tarsus length. They're all negative, which means that our bigger, chunkier, more floofy and adorable penguins are all going to have large negative PC1 scores. While the smaller, more adorable pocket-sized Gen 2 ones are going to have large positive score. So we can reinterpret and put context onto principal component 1 by thinking about what the relationship is between the original variables and the principal components. So in this case, principal component 1 is really just capturing size of the penguins. Now, that's just looking in the horizontal displacement of those vectors, but we could also look at the height in which they move relative to the origin. And this is where principal component 2 comes in. Now we're going to ignore the tarsus, the TML and the common length because they're really small. The displacement from the 0 is very minor, and we have two groups that essentially are big and probably have an important contribution to understanding the variation of principal component 2. We have bill width at the base, bill width at the goddess angle, and bill height. So essentially these are all traits that are associated with the bills, and they're all positive since they're above the 0 line. So this tells us that penguins that have big beaks are going to have positive PC2 scores. And individuals that have relatively small beaks are going to have large negative PC2 scores. So big beaks, small beaks. Now, the other things that we looked at so far are this radius length, the manus length, and the middle toe length. So these are all things that have big, important implications, but they're all pointing downwards, so there's negative loadings on them. So this means essentially those individuals that have long toes, long manuses, long radiuses, essentially big limbed penguins will have large negative scores, and those that have short and stubby little limbs will have large positive scores. So using just these two axes, I can describe a lot of the variation when it comes to the body size variation across these different sites. And they've color-coded these for convenience, but they haven't done any sort of statistical tests on them. So if they were to do that, what they would want to do is they'd want to take the scores of the rescored values, because taking these from their original 9-dimensional measurements and do some analysis with it. So we would do that by using the cbind function. So I'll make a new thing called together, and I'm going to cbind. I'm just going to do this for the Penguin PCA true, but you can do it for either one you want. Scores, and I want to add that on, combine those two things together. Gen2, combine these two data frames together into a new data frame. I can take a look at, and now I have my original columns, and I have these new axes on: component 1, component 2, component 3, component 4. And then I might want to do some analysis. I want to compare between my different sites. So I might go to plot together. I could pick my response variable is going to be component 1. And I'm going to say I want to compare my different lineages. Now sometimes the cbind function does some weird stuff to our categorical values. So just to make sure it works, I'm putting it within the as factor wrapper. And if that has worked, I can now see visually what my component 1 scores are. So I can see, and if you remember, that according to my loadings from up here, that these were all positive loadings. So I would say that my Falkland Island ones look like they're bigger than these other locations. But in order to determine whether that was statistically significant or not, I would need to go ahead and do the standard things which we would do when we're dealing with more than 2 or more groups. Looking at normality of each group, the equality of the variance, and then determining which one of the various parametric and non-parametric tests that we have at our disposal that we could use to answer these questions. I hope this has been helpful. If you need any questions, drop me an email. Please come by student hours, and I'd be happy to help. Good luck. Talk to you soon. Bye.